Before I reinstall the relay and the power supply board, let's take a look at this scale. The frame is die-cast aluminum, heavy, vertical riser here has mounted on it as bullseye level, and there are two adjustable feet up on the front of the scale, one fixed foot in the back. And using this adjustment, I can raise and lower these two legs, and by using a combination of both of them to raise or both of them to lower, and then a left and a right, I can center this bubble. It's rather important that the bubble be centered, and we'll get to that in a minute. This big block is the load cell. It's a circular steel container mounted or sandwiched between these two steel blocks. This one looks to be 3/8 and this one 1/2 inch. It's mounted on a 1/2 inch plate down here. It has massive risers supporting this mechanism up here. I'm going to call this the top of the load column. Now this is a tapered fitting. It is a fitting, even though it's just a chunk of metal. You can see it's tapered. The reason it's tapered is it accepts this female taper in such a way that this plate is held normal as at right axis to the center of the column. Being a tapered fit, it doesn't have any movement left or right, side to side. The column is cylindrical, and it goes down into this sleeve down here. There we go. And the sleeve has what appears to be a perhaps Teflon bearing in it that allows this column to ride up and down. Now the total movement is well less than 1/1000th of an inch, but it helps if you think that this thing moves up and down with the weight applied. So the weight is applied to the top of the plate, which is transmitted to this column, which goes down imperceptibly, unmeasurably almost, but it goes down. It cannot move left or right, forwards and backwards, because of this triangular mechanism. It's very rigid here. These brass rods are thinned out 4 places and have holes machined in them so that they're flexible. So these tend to form a triangular stabilizing brace. Of course, down inside the telescoping tube, that supports the bottom of the column, so it can't go anywhere but up and down. The column at its base is fixed to this metal hanger here. Get my fingers out of the way. It's fastened at that end to the column. So if I push down on the column, it tends to lower that strut. The strut's connected to this triangular frame, and the frame comes back and hinges here and here. Probably on hangers that have a glass wedge on them. Made it into another piece of glass, two pieces really. When a downward force is transmitted up this strut, that works downward right here. These two legs of the triangle cannot move vertically. Well, they can rock, they can't go anywhere. And so, any force here, not here, the force here is downward. The force here is downward, but on a separate triangular object. This rocks and transmits, actually it multiplies this force by the ratio of these moment arms. And that multiplied force is applied here to the load cell. So you have a complicated force transmission device where a load is placed on here. The force resultant from that is transmitted to this cylindrical column. It comes back up and is transmitted to here, and then this seesaw arrangement transmits it to here. It appears that the electric signal, if you will, is perhaps digitally transmitted through this ribbon cable to here. If this was just a 3-wire device, that is plus minus in signal, with signal related to the minus lead, a 3-wire device. But it's not. It's probably digital, and a parallel signal is transmitted through this ribbon cable. Here we have the on-off mechanism. Over here, there's an arm extending. This is somewhat symmetrical, except over here, there's an arm extending, and then there's two gray micro switches, one above the other. In this position, neither micro switch is activated. I push down on this bar, the upper micro switch contact closes, energizing the power supply, which will have a relay mounted on it. That relay contact closes and maintains the power to the device. Lifting up on this opens the contact in the bottom micro switch and depowers the device. Now, when I push down on this, a couple of things happen. If the device is powered down, and I push down, this micro switch, the gray one, activates this machine. This micro switch, through this little tiny piece of ribbon cable here, causes the board to zero the digital display. If this is powered up, and I have a load applied here, a weight, I can push down on the switch and it will tear the device, thus making the display read 0 and the weight, say it's an empty beaker, and I want to weigh the contents. I want to, what they call tear, the weight of the beaker. I'll set it on here with the scale turned on. I'll push down and I'll tear it. Lifting up causes the lever to activate the lower switch and turns it off. As I said in the previous video, I had to get this from Poland. And other than my name and some delivery confirmation, everything else is in Polish. So we'll open this box and take out what I hope is the relay. This is the relay, or at least the cover. I demolished the relay, tearing it out. So this is the one I removed. This is the one I purchased. Date code, but makes no sense to me. I put the power supply back in after I put the relay in, and this is I believe supposed to be the 24 volt power supply. And see, we have that's a stray reading, 0.8 of a volt. I'm going to turn it on. And you see it went up to 31 volts. I'll lift my finger off. 31 volts stays. So, I think this is good to go. Oh, well. It latches on now. Let's find out whether it actually tears and put a test weight on it and see if it is meaningfully right. Alright, I've centered the bubble. Turn it on. Turn it on. You see it's wavering around a little bit there. I think that's just warm up. So there it seems to be a lot more stable. I think it's just a matter of letting it warm up a little bit. And it hasn't been used for 10 years at least. So I think I'm going to let it sit powered up and see if it stabilizes a little bit. It's been maybe 20 minutes. And stays in tear reasonably well. If anything, it's dancing negative, but not enough to be 1/10 of a digit. So I'm going to place this disc on top of where it belongs. And then I'll place this plate Okay, so that's what the scale less the shell is going to look like. Those two devices weigh 213, I believe it's grams. Yes, grams. So I'll tear it out. See how it does with that. That looks pretty good. I have a set of, these aren't calibration weights, these are Chinese. This is 1,000 grams. Well, I'm sorry, it's 100 grams. And that's certainly, it's probably half of the least significant digit on the display, 100 grams. Here's 50 grams. Still the least significant digit. And a 20. And a 20. And I don't know what this is. It's a little tiny fellow. Probably 1 gram. This is 2/10 of a gram. So I would say, all in all, this scale, at least within the limits of my weighing capacity, is fine. This is 10 grams. We have 200.2. You see it's bouncing. And just see what it looks like when we tear it. Read 0. I'm going to start plucking these things off and putting them back. So I removed 2/10. I removed 1. 1.2. It's better. It's better in the negative range than it is going up. Take off 10. 20. 20. 50. All right, I'm now up. I've got a whole 1 grain error. I'll take the 100 off. So it's 1.2 or 1.1 in the negative. Now, I'm not saying my calibration weights or my standards are that accurate. But I'll tear it again. That goes to 0. Close enough. This is not bad for $20, 20-year-old scale. That is, it's 20 years old to me. It could have been 20 years in service when I bought it. So Please remember to give me a thumbs up. Thumbs up. And leave a comment. It certainly helps my YouTube status. For those of you that might be interested, these are the Chinese standard weights.